Flat Earth superstars. If you have ever driven a car through the night, you might have noticed this effect. The further away another car gets, the dimmer its lights appear. There are two factors that create this effect. First, the atmosphere always swallows a little bit of the light. The longer the distance, the more light gets swallowed. But there's another, much bigger effect, the spreading of light. Imagine a candle. Its flame has a certain brightness, but it spreads its radiation into all directions, so that the radiation density diminishes with distance. And because we can imagine this as the surface of an ever-growing sphere, the brightness of the candle even diminishes with the square of the distance. This is called the inverse square law. Now let me show you a line of candles. Where I live we call them tea lights, and you can buy them in dozens. I took random candles and put them in an almost straight line onto the table. Then I photographed them while standing in front of the center. From my observation point, the distances to the candles varied a bit, although not so strongly as perspective makes it appear in this image. Then I put the image into a program called Visual Spec. This program looks at the picture and sums up the brightness values for each column of pixels. This is called object binning. The result is a summed up brightness curve from left to the right of the image. Usually this program is used for spectral analysis. When I put my candle row image into Visual Spec, I also get such a curve. Of course, you see more brightness in the columns where the candles are, but you will also notice a trend that candles in the center appear brighter than the ones on the outside. Let's put in a trend line. In a more precise experiment you could calculate brightness versus distance and would derive something like the inverse square law relation. To make a long sentence short, the closer a light is, the brighter it is. This principle not only works for cars driving away from us, but also for bright objects passing by. Imagine the candles fly by. The effect is stronger when the differences between distances is bigger. Please keep this in mind. Now let's consider a flat Earth. The Flat Earth community claims that our plain planet has a dome that somehow limits the distance to the stars to some 10,000 miles or so. A person standing on the equator will see a certain star move from east to west right above his head. So let us draw its trajectory and move it a bit. What would a person see? During its journey, the star would constantly change its distance to the observer. It's the same setup like those candles on the table I showed you earlier. So we should expect to measure a similar trend line. How would that look like? A bit like this. The star should get brighter when it approaches and dimmer when it departs. And what do we see? Something like this. We do not see a big difference in the brightness of a star along its course, so we can conclude that the distance to a star is not really changing. This can only work when the star is very far away. many magnitudes further away than the flat Earth model allows. But it gets weirder. A star directly above a person at the equator is closer than a star above the person at the North Pole on a flat Earth. And a star above a person, say in South America, would be much closer. But wait, when this person in South America looks at the horizon, the stars should be even closer. Remembering what was said about apparent brightness and distances, the sky over Argentina should look something like this in the southern direction. Do we observe this? I don't think so. Because the stars in this direction are not closer than in any other direction. This means they must be very far away, and I'm talking light years here. But there's another problem. Do you remember the candle? It radiates not only light, but heat as well. If you have ever made a campfire, you know that it is very hot close to it, cozy, warm in the Goldilocks zone, but you won't feel its heat far away. Now the problem. Although flat earthers could argue that stars are like LEDs and don't emit any heat, they cannot say that from the sun. Let's listen to Eric D. from T.
132. The sun's light is golden, warm, drying, preservative, and antiseptic, while the moon's light is silver, cool, damp, putrefying, and septic.
So the sun does emit heat, and it does it considerably over at least 3,000 miles distance. That stirs at least 3 questions. How hot must the sun be on its surface to do that? What makes the sun so hot? And how does the atmosphere cope with it, if the sun is within the atmosphere? Let's have a look at that campfire again. At any moment it radiates away a certain amount of energy. The measure of this is called luminosity. Its unit is a watt. When this energy wave front gets further away from the source, the energy gets dispersed. Only a certain part of it hits a certain area, say a square meter. The measure for energy per square meter is called flux. Its unit is watts per square meter. The same goes for the sun, even on a flat Earth. Knowing those basics, we can calculate the heat of the sun. In Greece, where it is nice, warm and cozy, they usually get 800 watts per square meter of flux. So if we assume that the sun is only 3,000 miles away, we find that its luminosity is 2.3 times 10 to the power of 15 watts. If we further assume that the sun is only 30 miles in diameter, we get a surface flux of 314,082 watts. This corresponds to a temperature of about 5,500 Kelvin. And now imagine a fiery ball the size of Chicago of 5,500 Kelvin within our atmosphere. It would be a localized heat that would cause huge differences in air pressure, causing severe storms underneath the sun. Because of the sun's angle and the fact that the sun comes closer and gets away from us again, we would have much bigger temperature differences over the course of the day. Because of this localized heat, we would have much more air convection underneath the sun, resulting in charged up clouds and constant thunderstorms with lightnings. No way we could get a clear sunny day, not even in Greece. Clouds would gather along the path of the sun. The temperature differences between equator and moderate zones would be much bigger. Do we observe any of this? I don't. But when we assume that the sun is far away and heats up our planet more as a whole, those problems disappear.